Hello, this is chapter 17. We're covering immunization. Um, there's just a few quick points that we need to cover in this chapter. So I will make it very involved. Um, we start with the understanding of active versus passive immunization. So active immunization is any immunization in which your body or somebody's body had to launch an adaptive immune response. That is active immunization. Passive immunization implies that somebody is receiving gamma globulins, antibodies, something that their body did not have to launch an adaptive immune response and become active in the persecution of an infection in order to achieve that protection. Okay, so the main example of passive immunotherapy is usually antibodies. Um, we talked last week about the way that immunoglobulin A gets passed from the mother to the infant. That is an example of passive immunity that the mother bestows on her child for protection. Um, passive passive immunotherapy, antibodies, is something that we cannot ignore. It is something that is very, very, very useful. To give you an example, I think we talked about antivenoms. Okay, so in an antivenom, if somebody has been bitten by a snake, they have to have an antivenom delivered. And this antivenom are antibodies. It's passive immunity. Those antibodies recognize the venom, they adhere to it, they neutralize it, and it renders it useless, effectively saving the patient's life. Okay, so when you have a poisoning or we have a poison of some sort, a venom of some sort, then passive immunotherapy, the use of antibodies, can be a life-saving event, literally from one moment to the next. So these are instances where minutes and seconds count. So again, take-home message, the fact that protection against disease and toxins can be carried out immediately through antibodies or passive immunotherapy. Here's the author's argument for the effect of vaccines on the population. You can see this is polio, this is measles. Measles is in the news again. Can you believe it? And interestingly, is tethered to this problem, and that's the fact that there's people walking around that do not believe in measles immunization, and consequently, we're ending up with measles. I mean, measles. It used to be we were under the impression that that was something that we're never going to have to deal with again. And here we are dealing again with it because of people's ideas regarding vaccination. But you can see the incidence of polio up here, the first and the second time that the polio vaccine got introduced. Quite a dramatic change, going from 40,000 down to almost negligible. Okay, that if this doesn't demonstrate the effect of vaccination, then what will? Here's measles. Okay, we're talking about 700,000 people with measles. And then once the vaccinations were introduced, you can see that we still had maybe 50 to 100,000 cases, but over time that came down to almost negligible. So again, a demonstration that immunization does in fact work, and it is very, very effective. Okay, we're going to talk about the different types of immunization. There's a spectrum of immunization. On the one side, we have the most active form of a vaccination that we can have, which can be a live microorganism that has been rendered non-pathogenic. Okay, incredibly, that is typically the most desirable type of vaccination. What happens is that you actually get the infection, you actually get a little bit sick because you're infected by that vaccination. However, because the organism has been rendered non-pathogenic, your body is able to reconcile the infection easily and quickly. But because it was an active infection and it jumped from cell to cell to cell, the adaptive immune response launched by the body is very powerful. And because you're using an entire organism, the number of epitopes that are presented are many. It can be in the hundreds, okay? So that means that you're going to end up with hundreds of memory cells against this organism. And if you ever end up running into the future, your body is going to be able to react very, very well. So that's actually the most desired, okay? And then the spectrum moves from there to the right, in which we come up with killed subunit where they're smaller, molecular. In short, the size of the molecule that the body is forced to recognize becomes smaller and smaller, and consequently more and more difficult to keep on the radar, because the number of memory cells that you're going to have is going to be proportional to how many antigens or epitopes your body can discern, okay? And the smaller that a molecule is, the smaller that an antigen is, the less and less epitopes that your body can figure out, and consequently, the less memory cells that it's going to have. Unfortunately, a lot of things that we're protecting ourselves against are small subunit organisms, and so this is part of the vaccination that we actually have to continue. Okay, so your author starts all the way at the left with the most powerful vaccinations, which are attenuated. Attenuated means that, again, the organism is still alive but rendered non-pathogenic, so modified live. Okay, again, it can result in mild infections, and interestingly, that is desirable. Because of the many epitopes, you end up with many memory cells, and you end up with a strong immune response that lasts for a very long time. Okay. There's problems with it. There's problems. Not everybody can use an attenuated immunization. Those people that are immunocompromised cannot. So who are we talking about? We're talking about people that have HIV, they're very young, they're very old, those that are taking immunosuppression drugs, such as people that have had organ transplants. All these people have very weakened immune systems. And as a consequence, it's not necessarily desirable to use an attenuated vaccine on these people, because if a mild infection to a healthy person is not going to be a mild infection to them. So this is a problem, okay? And to prove the point, your author brings up polio, okay? So polio is an attenuated vaccine that we use sparingly in the United States. We've pretty much chosen not to use it at this point. And there's a couple of reasons. One is because there's a thing called contact immunity. Now, interestingly, with attenuated vaccines, contact immunity is desirable. What does this mean? This means that one person gets the vaccine, they end up with a mild infection, they become contagious, and that person passes that infection to everybody around them. And because of that, those people end up being immunized, even though they didn't take the immunization themselves. Okay, there's a word for this. It's called herd immunity. Herd immunity. So again, typically herd immunity is a desirable thing. However, if the vaccine is very powerful, such as in polio, having contact immunity is not desirable because we're concerned about that particular vaccine. Why are we concerned? We're concerned because it can revert to what's called a wild type. In other words, an attenuated polio vaccine has the probability, even though it's very, very low, but it has a probability of becoming pathogenic again. Let's call it reverting to the wild type, okay? And because this polio vaccine can become pathogenic, and because it can be passed from person to person via contact, those two reasons cause polio vaccine to be a cause of concern, okay? Now, how are pathogens attenuated? They can be attenuated by genetic manipulation. You take the pathogenic genes and you literally excise them out. You cut them out. Another way is you raise a pathogen through several generations in tissue cultures. And interestingly, mutations accumulate, and as a consequence of this, pathogenic traits have a tendency to disappear from time to time. When that happens, you have achieved attenuation of that microorganism. So those are two very useful techniques, okay? Now we're going to go from attenuated vaccines to inactivated or killed vaccines, okay? Again, because they're alive and these organisms do not have a metabolism, they are safer than attenuated vaccines. You're still getting the entire organism, but the organism has been killed. It has no metabolism. Okay, so again, these inactivated vaccines, they are whole agent vaccines. What does that mean? It means that it might be inactive, but it still involves the entire microbe. So that's important because what we're trying to convey here is that if we use the entire microbe, we're going to have the ability to use multiple epitopes and therefore form a good memory, cell memory. Moving on, we go to toxoids, okay? So a toxoid vaccine is a vaccine against a toxin. That's kind of what I started talking about when we're talking about snake venom, okay? Now, toxins are very small. They're molecules. So it's relatively challenging to send an immune response against a molecule that is small and renders very few differences from the rest of our body. And because of this, toxoid vaccines need to be administered multiple times to let the body go, okay, I know you've forgotten about me, but we need to build more memory cells against this toxin. Okay, so we're talking about small molecules, and as a consequence, we require multiple doses. Why? Because the toxoids possess very few antigenic determinants or epitopes. Okay, and because of this, they do not provide lifelong immunity. So you end up needing what's called boosters. Every once in a while, you can go in and get a booster. Okay. The next topic that I like to talk about is vaccine manufacture. Okay. We still use eggs for vaccine manufacture. Once upon a time, we used horses for passive immunity. You would inject the antigen into a horse. The horse would make antibodies against it. Then you would take blood from the horse. You would spin it down. You would take the serum and you would isolate the antibodies, and that would be the antivenom or the toxoid vaccine. And the problem with that is that back then, our isolation techniques were not very good. So it was very easy for components of the horse's blood plasma to actually be still involved with the antibodies. And if that's the case, the recipient of this vaccine would eventually build an immune response against this vaccine. Okay, How have we moved away from that? Well, now we're making hybridomas. Okay, so this is what a hybridoma looks like. You have what's called long-lived myeloma cells. Okay, long-lived means immortalized. In short, they're literally cancer cells. So one of the things that's interesting about some cancer cells is that they simply have no lifespan. So these are immortalized cancer cells. They're sometimes called HL cells for Henrietta Lacks. Henrietta Lacks was this poor woman that she went to a physician to get a checkout. She had some benign cervical cancer. The physician removed the cancerous cells without telling her. And then those cells became part of mainstream science research. Everything that we did, we contrasted against these HL cells. So if you're interested in that, Google it. It's very interesting. We've literally manufactured many metric tons of these HL cells because they're used in primary literature articles or because we use them in things such as hybridomas. Okay, so again, these are immortalized myeloma cells, immortalized cancer cells. And then what do? Then we take the antigen of interest, we inject it into a little mouse. Why a mouse? Because our scientific manipulation has gotten a lot better and we don't need as much blood as we used to. So we used to use horses. Now we can use a murine model because it takes very little to, with our contemporary tools, to carry this out, okay? So inject the antigen of interest into a little mouse. The mouse eventually creates plasma cells. B cells get turned into plasma cells against that antigen. We isolate those plasma cells, okay? And then we go through the production of what's called a hybridoma. We join these immortalized cells with these active lymphocytes, okay? And we make a hybridoma. So hybridomas are formed by mixing and fusing plasma cells, the active B cells, and immortalized cancer cells, myeloma. The hybridomas are long-lived and produce antibodies. So now, once this has been done, you're done because these cells are never going to die. So as long as you keep them in a good nutrient bottle and you keep on feeding them nutrients and mitotic signals for them to continue to grow and proliferate, these things will continue to make specific antibodies. And these antibodies are called monoclonal antibodies because you have a whole bunch of cells producing clones of a specific antibody. Fantastic. And then our isolation techniques are much better. So you can take all these substances, carry out state-of-the-art high-performance liquid chromatography, and you end up with pure monoclonal antibodies. There's none of that nonsense of serum sickness that we used to deal with a little bit ago, okay? Now, having said that, when you inject somebody with antibodies, that is still a foreign substance. And occasionally people will, their immune system will not recognize, will not be happy with those antibodies. And they will launch an adaptive immune response. So it's important when passive immunity is being administered that the patient be allowed to remain seated nearby in the clinical environment for a good 15, some places require up to half an hour, but at least a good 15 minutes to make sure that there is an immunological reaction and that the patient does not enter anaphylactic shock, okay? because it can happen. All right. Now we're switching sides. We're talking about serology. So as your author says here, serology is the determination and presence of antigens or antibodies in the blood serum. And the reason that we're switching topics is because we're going to introduce ELISA, enzyme-linked immunosorbent assay, and point of care ELISA. Okay, point of care implies that these tests are not done in a clinical environment. You can actually do them at home. So if you look at your summaries, the summaries had to do with point of care and ELISA and the incredible things that you can test that at home. Okay, some of them had to do with cell phones being used to diagnose cancer even. Okay, so what we're going to be able to do in the very, very near future is going to be just incredible. Hypothetically, you can carry a clinic in your cell phone. And we're moving towards that day very, very quickly. So look at your summaries because this is very interesting stuff. And it all begins with serology, determining and quantifying the presence of antibodies and antigens in blood. Okay. So we start with one method, and the method that I'm interested in, which is agglutination. Okay. This is what agglutination looks like. Probably everybody has done it. If you have ever done blood typing, you have seen agglutination. So agglutination is when you put a drop of blood and then you add monoclonal antibodies against A, B, and Rh. And if your erythrocytes have any of those antigens on their surface, the antibodies will cause them to polymerize and agglutinate and precipitate out a solution, just like this Rh and this B. So this person is B positive. And we can tell because these two have agglutinated. Okay. So because of these agglutination tests, there's a threshold that allows us to calculate the concentration or the titer of an antibody to a specific antigen. Okay. So that's important to know. An agglutination test is what allows us to calculate a titer. What's a titer? A titer is a concentration, a quantitative measurement of the concentration of an antibody that is specific to an antigen. Very, very neat stuff. Okay, so here's a precursor to what we're talking about. Back in week 2, when we're talking about microscopes, I was excited about fluorescence microscopy. So here's your slide. Here's your antigen of interest. Here's your primary antibody. Here's a secondary antibody. Okay. And that secondary antibody, in this instance, is labeled with a green fluorescent protein. And then you can put it under a long wave UV light. It will fluoresce. And what happens? Your microscopy becomes diagnostic. It's incredible then. It was incredible then. It's incredible now. Okay. So that's another way of using serology or antibodies. Okay. One is to quantify them the way that we talked about here. Another one is to assess the presence of certain antigens. And then another one is ELISA. Okay. And I don't want to spend a lot of time on this because we're going to do ELISA in lab. Okay. We have an ELISA. It stands for enzyme-linked immunosorbent assay. I think that the laboratory handout, does a much better job in explaining it than this slide. Suffice it to say, there's a couple things that you need to know. Number one, ELISA can test for the presence of both antibody or antigen. That's very interesting. You can choose one or the other. What's another thing? Well, ELISA does not use green fluorescent protein. It uses an enzyme. Why do we care? Well, imagine that you have an epitope. Okay, you have an epitope, and then you have an antibody attached to it. If you have a single antibody with a single green fluorescent protein, and you put UV light on there, you might or you might not see it, because green fluorescent protein is not fluorescent enough to be detected. However, if you put an enzyme on that antibody, and now you add a substrate that once it goes through that enzyme, it goes from, say, colorless to blue, then that single antibody is going to break a whole bunch of molecules, and that well is going to turn blue, meaning that the presence of a single antigen causing a single antibody to adhere was enough to give a positive. Wow. So what does this mean for ELISA? It means that it is incredibly sensitive, very sensitive. A single antigen will give you a positive. What else? Well, it uses antibodies. What's significant about antibodies? They're very specific. So it either recognizes the antigen or it doesn't. The use of antibodies causes the assessment to be very, very specific. So there you have it. 3 beautiful things with ELISA. With ELISA, you can test for the presence of antibody or antigen. Because it uses an enzyme, okay, that means that the sensitivity of the test is very high. And because you're using antibodies, that means that the specificity of the test is very high. In the real world, it doesn't get any better. Well, I just lied, because we're making it better. If you look at your summaries, the summaries say ELISA, and then below it says beyond ELISA. So just when you thought it couldn't get any better, somebody came along and made it better. So this is incredible, incredible stuff that we have right now. Okay, this is what a positive test looks like in ELISA. It looks blue. If it's not blue, then it stays clear. And again, you can run the test for antibody or antigen. Very, very neat. Point of care testing. Again, point of care testing is incredible because an ELISA test used to be used in a clinical environment. A point of care test means that that same ELISA can be used at home. Beautiful. The one that everybody knows, of course, is pregnancy. Okay, so let's look at the ELISA for pregnancy. Here it is. So what we need to know, this is really an ELISA. It really is. The primary antibody is down here at the bottom. Okay, but it's very diffuse. The primary antibody has color on the stem, but it's very diffuse and you cannot see that color. Okay, up here we have an antibody. This is a secondary antibody. The whole purpose of these secondary antibodies is to catch the primary antibodies if they travel up. That's it. So you put the dipstick, the point of care ELISA, in a fluid. If the hormone of interest is present, they'll cause these antibodies to detach and begin to flow upwards via capillary action. Because the line of secondary antibodies is a lot thinner, that number of primary antibodies gets stuck in a very small region, causing the color on their stems to augment itself, and you see it as a line. Okay? If the hormone of interest is not present, then this primary antibody does not detach, it does not travel up, and nothing happens up here. Okay, so the magic happens when, again, the hormone of interest is present, the primary antibody attaches to the hormone, they both travel up to dipstick, and then they are all caught in a very narrow band by the secondary antibody. And because this band is so narrow, the diffuse color in the primary antibody becomes concentrated, and you end up seeing it. That's all there's to it. No magic. Incredible. Okay. So this is high technology that we can use at home. Very, very neat. Okay, and that's it for this chapter. Thank you for your patience, and I'll see you soon.